In this lecture, I'm going to give you a short introduction to some basic concepts surrounding environmental impact studies. So first off, what do I mean by an environmental impact study? Well, what I'll be talking about here and the papers you're reading will focus on are scientific examinations of the impacts of some usually large-scale anthropogenic impact on natural systems. Um, and almost by definition, these sorts of impacts are unreplicated. So we're looking at the effects of a power plant on aquatic insects and fish downstream, or the effects of a nuclear power plant on uh, organisms in the environment where the discharge uh, goes from the plant. So by definition, these are quasi-experiments. The ecologists don't get to randomly choose where they're placed, nor are there replicates. And so that causes some real problems in trying to discern cause-effect relationships following an impact being implemented. One thing I want to make clear is what I'll be talking about and what these papers focus on differs from the usual interpretation of an environmental impact study, such as an environmental impact assessment or an environmental impact study. Okay, those are done before a project is started, and the idea is to try to anticipate what the potential impacts will be. Now, of course, the ideas or the inference from that is likely drawn from other kinds of environmental perturbations that are similar to the one that's being proposed. But again, there's no manipulation, there's no change, there's no, in many cases, real measurements. It's simply looking at the area where the uh, particular project is being proposed and trying to anticipate the impacts, especially on threatened and endangered species. One of the key concepts that comes up whenever discussing environmental impact studies is pseudo replication. And this is the focus of Hurlburt's 1984 paper, which is the first paper that's assigned for you to read this week. I'll warn you, Hurlburt's paper is a doozer. It's very long. I'm not expecting you to read it and digest everything that's in there. I want you to get the key concepts that he puts forward. And that is, pseudo-replication is defined as the use of inferential statistics to test for treatment effects with data from experiments where either treatments are not replicated, though some samples may be, or replicates are not statistically independent. And we've already touched on this with basic experimental design, but basically what it comes down to is, in many cases in environmental studies, ecological studies, because of the difficulty of setting up truly replicated experimental designs, in many cases what we'll do is we'll implement a treatment in one area, say heavy grazing by cattle, and we'll have another area nearby that is not treated. And we'll go out and take lots of measurements on the impacted pasture that has heavy grazing, and we'll take a lot of measurements on the other pasture that has not gotten grazing, and we'll try to make an inference about grazing effects from those samples. And basically what Hurlburt is saying is that is a statistically invalid approach, that you are not using in statistical parlance the right degrees of freedom when you do your statistical analysis. And this really was a bombshell when it hit the ecological literature in 1984. And I heard that there was at least one PhD student who was denied his or her PhD at the last moment because her committee discerned that they had violated this pseudo replication idea, and therefore the results were invalid. So it really reverberated around the ecological community and had a lot of people buzzing. So let's go through some examples of what we mean by pseudo replication. So here's a classic example where you're going to do your master's thesis and you want to look at the impacts of heavy metals on survival of growth of some fish species. So you have a pretty tight budget. You go out and buy 2 aquaria that are same size, same heaters, same pumps, and so on. And you put 20 fish in one tank and 20 fish in the other, and then you put your toxin or heavy metal, whatever it might be, in one of those tanks, and you measure those 20 fish for the next several weeks to look at either growth rates or how many survive. And at the end of it, you say, aha, I've got evidence of this effect of the heavy metal on my fish species. Well, there's a real problem with that, and I think all of you could probably see that right off the bat. And that is that really you only have one replicate of your treatment and one replicate of your control. You might think that those measurements on each of the 20 fish are true independent replicates, but that is not the case. All of those fish are in the same tank. They're all experiencing the same conditions that are present in that tank. So you can see here, one of these tanks is closer to the window than the other. That might produce more algae, which will make those fish either survive or grow better. The heaters may not be exactly the same, so one tank may be warmer than the other. The pumps could also differ. You could think of any number of differences between these 2 tanks, which would result in some change in perhaps what you're measuring in these fish in the 2 tanks. So this is, I think, a pretty simple but really exemplifies the real issue with pseudo replication. Is you can't just do one treatment and one control and measure each one several times and think that you actually have independent samples for analysis. So let's go to something a little bit more realistic maybe for the kinds of things we do. Here's a wind farm, and you may be interested in the impacts of that wind farm on bats or raptors or any other number of things that you might be measuring. And you could go out and sample that in a whole bunch of different places and then find another area nearby and do the same thing, sample in the same way, putting your antibat detectors up or whatever, and measure those over time and say, aha, I found a difference, therefore the wind farm is having an impact. Well, there's a problem with that. There may be pre-existing differences between the 2 sites that you choose. So the differences you might find may have nothing to do with the wind farm, but to the fact that there's more forest cover, more grass cover, whatever might influence the species that you're interested in the 2 places, and not due to the wind farm itself. Now, there are statistical approaches that we can use to try to ferret out these site effects, especially important that you could measure the same variables at a number of other sites outside of the wind farm and measure them over time. And those 2 things can give us a much better picture of whether the differences we find are truly due to the wind farm or could be due to simply temporal changes in abundance of a species or differences in vegetation communities between the 2 places. And then finally, a huge scale experiment, and this was back in the 80s when Hurlburt's paper came out, and that is the Exxon Valdez oil spill. And you can see here that it covered a huge area. The furthest area that was oiled was 470 miles from where the spill occurred. And you can see huge areas of Prince William Sound and the coast of Alaska, Kodiak Island, Alaska Peninsula were impacted. And there were lots and lots of studies done on fish, on otter, on seabirds, on marine mammals, looking at the impacts of the spill on those populations. And this had huge implications because Exxon clearly was at fault, and depending on the degree of the impacts that were found, that would dictate to some extent the amount of fines that they would pay as a result of this spill. So there was a lot of focus on this, a lot of good thought went into how you can assess whether the spill had an impact on particular populations. Once you are measuring, in most cases, you only had information after the impact had occurred. There was very few species that had been monitored in this area prior to the impact. So that added an even bigger obstacle to getting good statistical inference. Just some generalities about environmental impact studies. As I already mentioned, there's usually one treatment site, but that doesn't limit you to one control site. You could have multiple control sites, and in fact, a number of the papers you read emphasize the importance of doing that. It's clear, though, that in most cases, unless the area becomes very large, like in maybe the Exxon Valdez spill, that samples at each site are dependent. And this can happen spatially. If you measure a variable at one site and you measure it 100 meters away, those two measurements are probably going to be closer to each other than a measurement that's taken 1 kilometer away. So spacing of collection sites is an important consideration. Backy is possible. But as we mentioned, like with the Exxon Valdez, more often we're looking at a control impact kind of study, a perturbation, a spill, some kind of environmental catastrophe occurs, and then scientists are brought in to look at the treated area and the areas outside of that to assess what the impacts were. A critical part of this is selection of your reference site. Obviously, you want to match the site as best you can to the impacted site. And as I mentioned, multiple reference sites are better. You could also add a temporal dimension to this, and that is that measuring your response variable over time, both at the impact site and at the reference sites, will also then give you more insight into whether that effect or that difference that you're seeing is actually due to the impact. And then a final thing, that many of these are large scale, and because of the large scale, that could mean that results or measurements from smaller scale studies that are maybe on the order of square meters to maybe tens of square meters may not capture the impacts that you see from this very large perturbation. So studying the impacts of a small little oil spill on one beach and how that affects the otter or the fish or the even the marine invertebrates may not scale up to a huge spill like the Exxon Valdez spill. I think that should be fairly intuitive. Now, that's not to say it can't provide important insights. If you find that there are certain species from these smaller studies that are particularly sensitive or that show a big response, then that can be very important for looking at these larger studies. But there can be some real limitations with trying to extrapolate from smaller scale to larger scale studies. And I want to finish this with just a quick summary of what we call mixed effects models. And these are used for a variety of different approaches, but have especially been useful in impact studies. And I didn't talk about mixed effect models when we went over experimental design, so I just want to briefly introduce the concepts here. So a fixed effect is defined as a level of factors that can be replicated in another experiment. So a good example would be amounts of fertilizer applied to agricultural plots. You want to see how much this fertilizer affects growth of wheat or corn or whatever you're interested in. So you carefully measure out how much you apply to each of your plots so that you can make sure that you're putting out the correct amount in each situation, and that if you were to do this again, you could exactly replicate that treatment that you're applying. Something more relevant to the kinds of work that we do might be the amount of flea dust that's applied to prairie dog towns. So maybe the amount of pesticide that's dumped in each burrow or something like that. Something that could be replicated if you were to do this another time. A random effect refers to values that are drawn from a larger population. The values would not be repeated if you conducted another experiment. So in our first example of a pseudo-replicated experiment, we talked about the individual fish in a tank that was treated with a toxin. If you were to do that study again, you would get a whole new collection of fish and stick them in another tank and measure how they responded. Generally, random effects are not the effect of interest. In other words, you're really not too interested in the differences in how individual fish grow, for instance. But by taking that individual variation into account in your statistical analysis, you can come up with the appropriate way to test the effects of the treatment. Another example would be forest patches in a regional analysis of habitat fragmentation. So you might have a big area of the Midwest. You want to see what the effect of habitat fragmentation is on birds or amphibians or mammals. And so you randomly choose a number of forest patches from that region and go out and measure species richness or whatever you're interested in those patches. And you maybe measure that over time or look at other kinds of factors that may be influencing those species. And again, you're not so interested in the particular value associated with a forest patch, but you want to look at the overall regional effects. And again, if you were to do this study again, you would pick a whole new set of patches. So mixed models are situations where you have statistical models that include both fixed and random effects. Generally in these models, subsamples are treated as random effects and the impact is treated as a fixed effect. And this removes some of the issues that we may have with non-independence of those subsamples. So it's generally a much better way to analyze these kinds of data.